So we ended with this schematic of the ribosome and ribosome initiation of translation. And it begins with this tRNA, which recognizes the start codon, methionine, and the small ribosomal subunit. And a lot of figures in textbooks just have a random GTP being hydrolyzed as far as energy expenditure, but they don't really talk about what that is. I wanted to go into that a little bit and try to demystify a little bit of that process. We won't go into every single step in detail, but before I do that, I'll make sure that we all know the different pieces we're talking about of the ribosome. You have these EPA sites, the A site, the amino acid site. Some people call it the acceptor site, but it's the amino acid site. P site is the peptidyl site, and the exit site, which is where the used tRNAs are released. Just so we be familiar with these terms. So, to kind of get into what's actually going on here with this GTP hydrolysis, I wanted to go over this pathway, and this is, although kind of crude as a schematic, it's I think has the sufficient detail for us to understand exactly what's going on in the process. So, it begins with our initiator methionine, right? The methionine attached to the initiator tRNA, and it binds to a heterotrimer called EIF2. Probably heard many times, we'll go over EIF2 alpha. It's a kind of a canonical symbol or signal for when there's stress in a cell. We'll get into that. But these two components come together and make a complex that then binds with the small ribosomal subunit. And these start at the beginning of the message, and in combination with the EIF4 helicase, starts to melt that RNA so that this complex of EIF2, the GTP, initiator tRNA, and the small subunit, scan on the message looking for the first start codon. And once they do find this, this is, kind of think of it like a decision or step, right? So we have multiple pieces having to come together at a certain spot to make a decision of like, this is where we're going to start translating. And that's an important decision to get right for the cell. And so once this has happened, you have kind of a licensing of this start site. So the hydrolysis says, this is the spot to start. And that hydrolysis then allows the recruitment of the large ribosomal subunit. So then they all come together. But different cartoons will kind of show this in a little different way, maybe to simplify it. But you essentially license it after the hydrolysis says, click, this is the place. You can now bring in the real important catalytic machinery, and then we can start the process of translation. But we do have to deal with recycling of this process, right? So we have this EIF2 GDP. Obviously, it's a common theme we've hit on many, many times now. We have to recycle this, and in this case, we use a GEF called EIF2B to exchange out this GDP for a new, fresh GTP, so that the cycle can repeat again. And so, because this is such an important step, this is generally critical points in pathways or points of also intervention where you can say, well, there's a problem, we should stop all this translating now and figure out how to deal with this other problem before we start wasting any more energy, especially if we're already starving. And so, a phosphorylation event is known to occur on EIF2 alpha as one of the subunits of this heterotrimer, which we call just generally EIF2. So, does anybody have any questions about this cycle and what's going on, right? We have this complex with the small ribosomal subunit, scans, finds the start, hydrolyzes the GTP to GDP, licenses it for recruitment of the large ribosomal subunit, then we can start the translation. But to recycle this component, we have to bring in the help of a GEF to essentially recharge this so that the pathway can continue. We can have reinitiation every time this way. Anybody have any questions about this? Yes?
How long does CBIO actually stay on the DNA? Or does it disassociate like a secondary reactive?
As far as I understand it, once this thing is hydrolyzed to GDP, it is then released from the tRNA. So it's kind of a, I guess, as I understand it, it's a kind of a delivery mechanism. It says, okay, we'll deliver the tRNA. Once you're in the right spot, everything's assembled. I'll release. Maybe that opens it up for recruitment of the large subunit. Otherwise, it's maybe sterically hindered by that. Yes?
I was going to ask, it's the line that points from the phosphorylated CIF2 to the CIF2 read, does that mean that phosphorylation is inhibiting the GEF activity, or?
That's a good point. So what is thought to occur when EIF2 alpha is phosphorylated is it actually doesn't allow it to interact anymore with the GEF. So it bars that interaction. So it acts like a block. These kind of bars that we use a lot in these pathways sometimes aren't quite clear, right? It's not sure. Is this inhibiting EIF2 beta B from being a GEF? No, it just stops it from being able to really bind to the EIF2 and stimulate exchange of the GDP for GTP. Good point. So if this is kind of a canonical Western blot of what happens in a cell that's undergoing stress, and if we look at the phosphorylation status of EIF2 alpha, and what I want you to realize is in these kind of Western blots, when we're looking for a particular change on a protein, we first have to know how much of that protein is there total, and that's what this bottom antibody is detecting, just total EIF2 alpha. Then we have very special antibodies for the phosphorylated form of EIF2 alpha, and this detects the serine 51 phosphorylated form. And so what this shows us is that when we do have stress in the cell, nutrient deprivation, this is phosphorylated heavily. And this puts a halt to any new energy expenditures of translation. And we can't recycle this. And it inhibits this GEF interaction that we talked about previously.
All right, quick question.
Yeah.
Why do we see an increase in the total EIF2 alpha with stress?
Well, I would say that's a more minor increase. But yeah, it isn't a perfect loading. Whoever did this gel didn't perfectly load the exact same amount of cell for EIF2 alpha. But in general, the relative difference suggests that phosphorylation is going way up. Yeah. Scientists aren't perfect. So, any other questions about what we're seeing here in this Western blot? We have a loading control of a sort which isn't 100% perfect, and we have a phosphorylated version that we're detecting differently with a different antibody. Okay, so we've initiated the translation, right? The first amino acid is now in the P site, right? The tRNA of the initiated methionine. And so what I want to go is, successive rounds of GTP hydrolysis that bring in the new tRNAs to essentially extend the new peptide that's being synthesized. So we'll first start at the step 1 in And you see this GTP hydrolysis step. And what we're looking at here is another protein. It's kind of like EIF2, but it's called EF1. This complex brings in the tRNA, the next tRNA. Once everything is assembled properly, it hydrolyzes, licenses that tRNA to be there. So everything has to be the right tRNA for the right codon. Says, okay, this is the right one. We release through GTP hydrolysis, make sure that's everything's correct. Now you can have the peptide bond being formed between the methionine, the new amino acid, and it's the first amino acid, or the second amino acid being added. This EIF1 alpha departs. You have the second step. So now we transfer, right, this from the initiator methionine. Not in this case. There's already several amino acids here in purple, but this tRNA gives the growing chain to the new tRNA, attaches to that amino acid, and then this one becomes freed up. But then we have another energy expenditure step, which is EF2, bound to GTP. What this does is has the effect of moving the ribosome down one codon. This moves what was in the A site tRNA, with the growing peptide chain, moves it to the P site, and now the old tRNA is moved to the E site, the exit site, it's sent away. Right? So we have two GTP hydrolysis steps per amino acid being added. So you can see that happens for every amino acid being added. It's quite an expensive process that you're getting into by doing translation. Anybody have any questions about this pathway? Okay, so just to review, what we're building here is a peptide bond, and we'll get into more of this in the next section after we finish this. But just be aware of what that bond is and how it looks. And so we have initiation, elongation, termination. Now termination is a little bit different. It doesn't use a tRNA, it uses a protein called a release factor. And this recognizes the stop codons. And it uses two GTP hydrolysis steps, which we're not going to go into, but one is essentially to break that peptide bond. Another is to dissociate the ribosome from the message. But I'm not really interested in knowing this particular step. But it is a different kind of recognition. So it's a protein recognition. We'll talk about that at the end of the next section as well. This is an interesting little video about translation. It is hyper simplified and much more cartoonish, obviously, than it really is. So let's see, what we see is small subunit of the ribosome. So it is in complex normally with the EIF2 GTP tRNA to build the kind of the complex that scans for the start codon. But once it's been licensed, you have recruitment of the large subunit to make the full catalytic machine. We see the A site, P site, and the E site in this cutaway view. And after this has been licensed, in the initiation step we have elongation. We bring in a new tRNA, which is charged with an amino acid as its anticodon. Comes into the A site. formation of a new peptide bond, release from the old tRNA, and then you have movement of the whole machine forward one codon. Move this into the P site and get rid of the old tRNA. And this just happens over and over. So what I wanted to get into, oh yeah.
Does energy have to be expended to create the peptide bond, or just holding those amino acids close together just happens by itself?
Right, so I mean, in a sense, and we'll get into this when we talk about charging of the tRNAs, which is what most of this section is about. Energy is kind of front-loaded in to kind of pre-activate these molecules. So that bond is already kind of high energy in its sense when it's charged to the tRNA. So, yeah, nothing's free. Right? So we looked at this schematic the last class, and I kind of want to go into how the cell charges tRNAs, how it does this accurately. So this is kind of what we assume to be the actual structure of the tRNA. Now there are ideas that you've heard before, which is this kind of wobble, the degeneracy of the codon usage, and I want to kind of go into a little bit, why that is, if you haven't already discussed it, previously in classes. But this is our anticodon, right? And remember, it's reading backwards, so this is the wobble base, and the reason is wobble bases. You have this stacking of bases, and as you remember from chemistry or organic chemistry, that you have this stacking base creates these pi bond interactions, which help stabilize their rotation and their conformation in the molecule. So these guys are much more stable because they're kind of hindered from rotating easily by the bases around it. Whereas the last one is kind of free, and it can actually wobble a bit, which is why we call it that. It can move around, and that creates some flexibility in the bonds that it can form and the codons that it can recognize. So there are the consequences of this are seen in the code. Oh, I did want to mention something. No, I guess that's not here. So in the last lecture, we were talking about how to read those codon charts. But that one thing I realized later was that chart on the left side, with the more box chart, not the circular chart. That's actually, I don't know how that happened. It's actually mislabeled. So that's where it says the first base versus the second base. Those need to be switched. So that's a wrong table. So I'm not really sure how that happened, but just keep that in mind. You can't actually find the amino acids per codon from that chart. It's a little bit backwards. Okay, so we're going to touch on certain features of the tRNAs. I want you to remember this amino acid binding site is going to be really important. It's on the 3' end, and it's always the same 3 bases. It's always ACC. This is the acceptor site. It's always an adenosine. We have, in this case, we have this UCA codon for serine, and it's read with a tRNA, which if you read it 5' to 3' is UGA, but we would naturally read it as a AGU anticodon. And so these are what people realize are what happens with the wobble base. Other things that it can base pair to. So G can base pair, if it's in the wobble position, can base pair with U or C. C can only base pair with G and A only U. But U can base pair with A or G. And inosine, which is a modified base, we won't go into detail about how that's made, but the modified inosine can base pair with A, U, or C. And so the question I have here is, what's another possible codon that could have been decoded by this same tRNA? So we have this UCA. What other codon could this decode? Or what other base can it decode? The wobble position base. Right? In this case, it's a U. That's right, UCG. So it's this U in the wobble position can decode either an A or a G. And so UCG also codes for serine as well. So be familiar with this chart. Now, Francis Crick is famous obviously with the DNA structure, but a lot of people don't know that he also went and did a bunch of other incredible things relating to how the messages are decoded. A lot of this stuff wasn't known at the time, and he was actually quite good at hypothesizing things that have to exist. And so he actually hypothesized the existence of the tRNA. He knew there had to be some kind of adapter mechanism to read and translate this message into an actual protein. So it was kind of first proposed by him. But these guys actually decoded the message, of what codons signify certain amino acids. And what they won the Nobel Prize for this. What they came up with was a way to essentially synthesize the RNA that they could then put in kind of an in vitro system and see what kind of amino acids were incorporated. And you don't have to know all these things, but they just generated all these different types of messages and found if it's CUC in different frames, it can be leucine or serine, and they just systematically went through it and found out what codons coded for what amino acids, and proved the Crick's hypothesis. So back to this structure of the anticodon. So we have this cloverleaf schematic that is pretty common, and these actual structures of how it really looks. And I said, I want to focus on this stem here. Now this is, all tRNAs have this ACC receptor site, and this is where the amino acids are going to be conjugated to. And these are kind of an invariant aspect of tRNAs. And this is the anticodon. So what I want to, first we'll kind of revisit this degeneracy for a second. Why it's degenerate. So, and again, all these different cartoons will draw it a little bit differently. So in the prior one, we had the message going 5' to 3'. Here we have it flipped so that we read the tRNA 5' to 3'. So this is the wobble base, the C here. And this is conjugated amino acid to the acceptor stem, the ACC. And this explains how different tRNAs can decode different codons. Because you only need to make strong base pairs with the first two nucleotides. The third one can be a little bit off. And so this is a reiteration of that table where now they flipped it again. So you see now it's back 5' to 3'. This is the wobble base. So this UCU anticodon can decode AGA or AGG, and this CCI anticodon, this inosine, can decode all three of these. And this is just for your own knowledge of the different base pair orientations of the bonds between the bases. So one thing I want to kind of get into a little bit is how amino acids are charged. And so this gets back to the question before is, where's the energy coming from for actually making these peptide bonds? So the first thing we have to do is we'll take our generic amino acid and we have to charge it. We charge it by essentially fusing it to AMP. So we take an ATP, and this occurs in the tRNA synthetase enzyme, which we'll go into in a little bit. And so you now have this amino acyl AMP being formed. And then the amino acyl AMP is then transferred to the tRNA. So we have this charged amino acid in a sense. It is fitting into the tRNA synthetase. The correct tRNA comes, and this is a schematic of the tRNA. And again, at the end, we have that acceptor site, right, the ACC. This is a terminal adenosine. This is then bound, so this 3' hydroxyl is used to charge to and transfer that amino acid to the terminal adenosine. And we'll go over this a few times, so if it's not clear yet, hopefully it will be. So this is our the tRNA synthetase. This is the mock-up of the tRNA structure in this enzyme. And so two things to make apparent is, how does one synthetase know that it's the right tRNA? And so it recognizes both the anticodon and part of the acceptor stem to distinguish, the right tRNA that's supposed to fit into this active site of the tRNA synthetase. So you have to imagine there's probably a lot of them floating around. It only wants to bind to the right one, charge the right one. This is an important step in discriminating against the tRNAs that you don't want to charge. So we had that one schematic of the bonds simplified. And this is a cartoon version of that. So imagine we take this amino acid in purple. We have to charge it. That's the first step. We charge it with AMP, release this pyrophosphate. The next is your tRNA comes, and it's made sure it's the right one at the anticodon and the stem into the right tRNA synthetase. You then transfer this charged amino acid to the acceptor stem, adenosine, and then now you have your charged tRNA. It's ready to go and be used in translation. Does anybody have any questions about this process? What we're doing by charging it? First, have to pre-charge it, then we donate it to the tRNA. This is yet another kind of schematic of that, creating this high energy bond with the terminal adenosine of the acceptor site and the amino acid. And this is how it will be eventually selected by the anticodon and transfer the amino acid to the growing peptide chain. This whole thing is an amino acyl group. This is an ester, obviously. And this is what it looks like when it's attached to the tRNA. This is I don't know if we should really watch this, but it's extremely simplified view of this process, but I think it kind of makes the point. You have to charge it, right, with your ATP, the amino acid. This happens in the synthetase, releasing the pyrophosphate. You then have a specific tRNA. You want to add the right amino acid to it. It comes in, it's recognized by its codon in the acceptor stem. Someone's normally speaking in this, but then you have the transfer, releases that AMP that it was charged to, and now it's essentially charged to another adenosine. Now, an interesting problem which comes up is how this can actually occur when we have amino acids that look really similar to each other. So, tyrosine and phenylalanine aren't that different looking from each other, only a hydroxyl group. Isoleucine and valine also not that different looking from each other. And you can imagine that it could easily be a problem of charging the wrong amino acid to a tRNA. And so the nature has figured out a way to try to at least minimize this error rate. And so this is a mock-up of your tRNA synthetase. And so what it has is it has two different sites in it. It has an actual catalytic site where it charges the tRNA, but it also has a proofreading or an editing site. And so you'll have, say in this case, you'll have the incorrect amino acid being added to your tRNA. Right? So the normal reaction occurs, that ester group is formed, but it's the wrong one. And so in this case, we'll use the isoleucine synthetase as an example of how this process works. And so you have this, again, the synthesizing or the activation site. And what this does, this is what they call a coarse sieve, right? So it rejects anything that's larger than isoleucine. So things that are much larger than isoleucine can't fit in this pocket. Things that are smaller, like valine, can, but everything bigger, it's just like you can't. We're definitely not going to use you, right? So it's like a first way to eliminate the wrong amino acid. Then, say you do get the wrong one, then you have an editing or hydrolytic site, and this is what they call a fine sieve. And so, say you accidentally added valine to the tRNA, it now can fit into this editing site. And so, if it was isoleucine, you'd say, well, you can't fit in there, so we're not going to actually hydrolyze this and break this off. Only if you're smaller than isoleucine will you be able to fit in this editing site, and we'll cleave off the amino acid, and we'll try again. And so it's better to just try again than to go ahead with incorrectly charged amino acid. It could cause a lot of problems. And so this creates a much more faithful charging of your tRNA. Does anybody have a question about this fine sieve, coarse sieve idea and how that works? Yes?
Maybe already said this, but are there different proteins, like tRNA synthetases for each amino acid?
Right, yeah, there are. Yeah, so every amino acid has a particular synthetase for it. Yeah, it has to, it's very specific for one, because, yeah, a lot of variability, right? Yeah. So this one is the isoleucine synthetase, as in the example we're using here. Yeah, so everybody has their own. So, I want to take a few minutes to discuss this with a partner. So we have our first step where we charge. We have our second step where we transfer, and we have this editing concept for the fine sieve and the coarse sieve. Let's take just 2 minutes to discuss with the neighbor. If you have any questions, and we can kind of talk through this process and see if there's anything that comes up that doesn't quite make sense yet. You don't have any questions about this? It makes sense. So this one, fine sieve, only lets things that are smaller than it should. So in this case, if you put baleen on there, baleen's a little bit smaller than isolation. Baleen, so baleen fits in there, it's like, oh well, nothing should be able to fit in here. And so if something does come in here, we're going to cut it off. That's really hard. Right, so it won't fit. So you do the kind of first cut off with the coarse.
And they're coming up with 3 things that I find interesting and confusing.
Maximal size.
Leaves reflections.
No, I don't
Things that are smaller
usually.
could possibly be charged. And if that fits in our active site, we know it's the wrong one and we just cut it off. It would be bigger than isolation. It would be excluded from charges. Just wouldn't fit into the active site. It would just be staring hindrance. Well, it would just never get bothered in the first place.
I won't go
So it would just be excluded right away.
Yesterday I was asked if that was
Yeah, go ahead.
So in this picture it shows that it's bound to tyranny when it's like making sure the correct amino acid is bound, but then it says that it's bound to A and P at this point. But I thought that when you bind to tyranny, you're taking off the A and P.
Yeah, so this is released
Yeah.
after charge.
But in the slide before, it says accepts activated amino acids are stored in SODC but rejects the SODC A and P. So is it still bound to A and P at this point?
Yeah. So it's charged when it's fitting into the active site, and then once it's been transferred to the tRNA acceptor, that AMP goes off and it's released. So yeah, it's that the active amino acid, which is the pre-charged one, is bound to AMP.
I guess I just confused that picture, but
By this one or this one?
yeah, those.
Okay, so again, this is the coarse sieve, right? So anything bigger, any other amino acid which is charged, so we'll have tons of amino acids that are charged. If you're bigger than isoleucine, you'll never get a chance to even be added because you're just that much bigger. It won't even fit into the active site. But if you're valine, you're smaller than isoleucine, you can fit in here. Maybe we'll accidentally charge you with that. Then that's where the editing site kind of comes in and says, well, isoleucine, we want that. But if you're smaller than isoleucine, which is the other side of the kind of way we discriminate whether or not we've charged the incorrect amino acid, valine fits in here. Anything that fits in this active site, we're just going to cut off because it shouldn't be able to fit in here. And that's a kind of a way to make sure you don't add anything too big or too small to the tRNA. Any other questions? Alright, so this is just a revamp of what we've already talked about. So again, this is the actual peptide transfer, right? So you have this amino group which has this pair of electrons. You have the nucleophilic acid on this carbon. This creates essentially the amide bond between the carbonyl carbon and the amino group, and creates what we call the peptide bond. Oh yeah, so we touched on this in the last slide, set of slides, this idea of termination. And I think this is a cool concept of molecular mimicry. So the release factors, the crystal structures have shown us that the release factors actually look, although they're made out of protein, actually look a lot like the structure of the tRNA. So they fit into this, the A site of the ribosome, just like a tRNA would. And that's really important for its function. And so it's the protein itself has the ability to actually read. We have DNA binding proteins, RNA binding proteins, ones that are specific. And so it has the ability to actually read the sequence and reads the stop codons. Now, one point I want to end on is that a bunch of different antibiotics that are used in biology, we use these a lot in the lab. A lot of these antibiotics function to disrupt translation, and a lot of them fit into the active sites of ribosomes and cause premature chain termination. One that we use all the time, puromycin, it resembles kind of the 3' end of an amino-acylated tRNA, and actually catalyzes the same reaction that a peptide amino acid would do on the end of the tRNA. You can see this is the puromycin at the A site. It's having the same reaction occur to form the peptide bond as would normally occur. But what happens is now you have this other chemical group on the end that, of course, can't be used anymore, and so you kind of terminate translation whenever the puromycin fit into the active site during that process. So it essentially stop all translation, and that's an effective way of killing a cell if that's your goal. And so a lot of the drugs really that we use interact with this point in the process. And so what I want you to think about when we talked about these different processes of making the ribosome and the nucleus, we talked about these points of intervention where, we sense stress, we're going to shut down production of the ribosomal RNA, we're going to quit making any new ribosomes. We also sense stress, we're also going to shut down all translation, we're going to phosphorylate the initiation factors so that they can't be have GDP exchange for GTP anymore. And so these are kind of all ways that the cell senses the outside world and problems that are going on and stops certain processes so that it can kind of get its bearings again and fix whatever issues is occurring. So with that, we'll end a couple minutes early unless anybody has any questions they want to discuss.